Yeah. So what we'll start off with tonight is having a look at that energy analysis part of Project 3. So I think that's probably going to be the most important thing to look at. So yeah, sent out an email just a little bit earlier on this afternoon to say that I made the step-by-step guide and also provided a bit more information about doing that energy analysis and talking about due dates and all that sort of stuff. Pretty much the discussion we just had just now. And so if we scroll down to our research task 3 section, so you've got your research task 3 instructions, that's all good. Probably doesn't need any explanation there. Research task 3 office template, once again, should make plenty of sense to you by now. It's much like all the others, except it's got a little bit in the end for the energy analysis. So I'll download that and keep that one sitting there for when we need it. Assignment 3, drawings. I like to pull that. Awesome.
If you push stop presenting off the top, did that get rid of the thing just on
yeah,
the top?
but it will also
It does just
mean that it also mean
do the 3 buttons at the end come up with like an option?
maybe. Okay, let's just give those a shot.
Oh, drag it.
Oh yeah, interesting. Yeah. Anyhow, I'll just drop this. Yeah, drop that one down. Just ever so slightly underneath it. Relatively functional. So that's our drawings for the building. I'll get those up and handy. Then that's what's been added today. The energy analysis step-by-step guide, and there's also this information that was up there previously, the energy calculation information, and also the energy calculator. So there's a buttload of stuff for this one. Well, it's not that simple, it's a buttload of stuff. So we've seen the Excel file, except if I do that. Oh, there we go. We've seen this Excel energy calculator before. Super important thing, only fill out the yellow squares. Don't go modifying any of the equations within that or any of the formula in each of these cells. That one doesn't have formula, but that one does. The formula just makes it fill itself out automatically. Start mucking around with the formula, then mucks around with the whole thing. So just the yellow squares, and that will be a guide as to what information you need to find. And the only yellow square the only square you might want to muck around with the formula in is this one, which doesn't have a formula. That is how many years would it take for solar panels to pay for themselves. That is going to be answered by our total cost of panels divided by the cost per year of electricity. Obviously, if it costs me $100 to buy solar panels, it costs me $20 a year of electricity. It'll take you 5 years to pay for the solar panels. Pretty simple equation. What I haven't done is, I haven't given you that answer, but it's really pretty simple. You could go that, in there you go, equals that cell divided by, always divide by on this one, divided by that cell so that's our energy analysis spreadsheet. We'll revisit that again in a little bit. So have a quick look at this energy analysis step-by-step guide I'll put up today. So it's just simply a Word document. It says some of the things that I already said just now, but then it also sets out all the things you have to do for your air conditioning. So determine the area of the office space on level 1 that will be air conditioned, etc., to that. Once you've determined the square meterage, put this into the energy calculator spreadsheet. So I've worked out how many square meters go. Worked out how many square metres of office space on level 1 that we're air conditioning, and we just put that square meterage into here. So that step-by-step guide is as the name suggests, tell you this is what you do, this is what you do, this is what you do. And then also just as a bit of a background to that, let's drag that one down, have a quick look at our drawings. So you're meant to do your energy analysis on level 1 only, so get the first floor plan and work out how many square metres we're air conditioning. Now, the thing about air is it doesn't stay in one place. So whenever you've got open doors like this, if you're air conditioning this space here, you might as well be air conditioning this space here. So have a look at this floor plan and calculate within the nearest 10 square metres. We're not being exact with this. But use your dimensions to work out how many square metres this area is, how many square metres is in there, how many square metres is in this entire office space, and then this space here, and that will tell you how large your air conditioned space is. That's it. We don't air condition our stairs, we don't air condition our lift, server room, or toilets, or storeroom. So all of those areas which are locked off by closed doors, we're not including them in our energy analysis. Also, you're required to do lighting calculations for the office area as well. For our office area, we're just illuminating the office area. We're not illuminating the corridor or toilets, server room, stairs, etc. That comes under amenities lighting. Also required to do some amenities lighting calculation, or not calculation, that's really simple. You're just specifying 21 globes with 1400 lumens each. You research a globe that produces 1400 lumens and tell me what the wattage is, or how many watts of electricity are required to get that 1400 lumens. So we're just going to do our lighting calculation for our office area. So that, included with calculating how many solar panels you can fit on the roof, is all you need these plans for. So we've used the plan level 1 for air conditioning, once again for office lighting, and then we'll want to have a look at our roof plan for determining how many solar panels we can fit on there. Now, what you want to do is you probably want to refer back to your first floor plan here for your overall dimensions to get the dimensions of that building. Now, some of you are doing other subjects like compliance where you actually use these Revit models. If you've got that Revit model, that makes it a little bit easier because you can do your solar panel calculation by using Revit and placing solar panels. If you're not, Alana, do you use Revit? Yeah, no. That's okay. Can actually be a very simple process doing it the old school way as well, where you just maybe even draw this up on a piece of paper if you wish. Put in your dimensions and draw in your and calculate how many banks solar panels you can fit on there. The way we want to arrange our solar panels is we want to arrange them in banks of 2, so our solar panels will be I'll draw a square. I'll just quickly for you guys, I'll draw it up on there. Let's say really simple roof like this. We'll be wanting to put solar panels in banks of 2 like that, next to each other, and another bank 2. So lines like that, but leave 600 mil here, 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 etc. around to be able to access the edge of those banks of solar panels. So the solar panels can be butted up to each other in long lines, but a bit of space around the outside of those lines, 600 mil for servicing those solar panels. And that's pretty much all you'll be needing the drawings for, is for that. So we have our step-by-step guide to that. I think I've written it fairly well, so you should be able to follow that quite well. So I won't go into that any further, but what I will have a look at with all of you is we'll have a look at this energy calculation information. We'll go through that. So the presentation, brief introduction to electrical power consumption. The following topics will be covered: electrical energy, lighting, air conditioning, computers, refrigerators. So, fairly simple. Electrical energy is measured in watts, but because one watt won't really do very much, we don't actually use energy, or we don't measure energy in watts. We measure it in kilowatt hours. So that's by using 1,000 watts for 1 hour gives us 1 kilowatt hour. So you're paying sort of that 38 cents or something per kilowatt hour. So if you've got a 1,000 watt heater, you run that 1,000 watt heater for 1 hour, it costs you 38 cents. Simple as that. The old way of, I guess, looking at light globes, etc., was that light globes would always be expressed in watts. So you had your incandescent light globes, which are the ones with a little element in there that when it's turned on, it's hot. So hot it produces light. You could buy 100 watt, 60 watt, 40 watt, 25 watt, etc. Now, they would produce various different lumens, but because incandescents are pretty much the only globes available on the market, people weren't really looking at lumens. They're going, okay, we need a 100 watt light globe here, we need a 60 watt here. That's all changed now with the advent of so many different types of globes in the market, and now when you look at globes within your house, probably what you'll be looking at is you'll be looking at lumen output of your lamps. You might be looking at wattage, so you might be comparing lumens to watts and going, okay, well, this one's got lots of lumens, it doesn't use any watts, but it costs $20, etc. So you're looking at those factors. But you might also be looking at colour, temperature of lights as well. So you might be looking for a warm light or a cold light. Either way, typically, you notice that your cold lights are quite energy efficient and cheap. Whereas achieving that warm colour range is typically a little bit more expensive in your globes. So that's what you have to do for your own home lighting now. So for most people, it's not doesn't require too much explanation. But certainly with the advent of LED lights, you could produce the same lumens from 19 watts as it used to take 100 watts to do so with an incandescent light globe. So a bit of a chart there comparing lumens to light output for your incandescence versus these compact fluorescence and halogen light globes. Although this technology is getting better and better all the time, and probably that chart may even be a little bit outdated now. Probably take you less than 15 watts to produce 1100 lumens. So that's the globes, and that's what it's putting out. And certainly as lighting designers, it does get quite complex in regards to not only thinking about lumens that are required, but also the color temperature of the light, but also the direction of the light, the placement of the light. In most residential applications for your standard project homes, it's just simply a bayonet fitting in the middle of the room. That's the extent of the lighting thought. But when you start getting to upper end residential, there is a lot of thought put into lighting to create, create a feeling within a room, a sense of space or sense of enclosure, etc. We won't be going into that sort of thing. I'm by no means an expert in that. I've sort of got my own ideas, but as you will do. But what we are going to be looking at is just very simple lighting for within an office. So to ensure that people are carrying out tasks safely and also not straining eyes, etc., there are basic requirements for the amount of light that you have to have on a desktop at work, for example. That's covered in the Australian Standard 1680. So that in there, it's covering all aspects of interior workplace lighting. But the section that we're going to be looking at is Table 3.1, which goes into how much light is required at that desktop. So recommended maintained illuminance. So first of all, it'll be about having a look at that level 1. So our level 1, it's an office space. So we have to think about, okay, what's going to be used? It's going to be used for general office tasks. And then we'll have a look down this column here, looking at that class of tasks. So movement and orientation, rough, intermittent, and to gain a bit more insight into that, you can go, okay, movement and orientation. Interior is rarely visited with visual tasks limited to movement and orientation. So that might be a storeroom. It might be a passageway to the storeroom. Rough, intermittent. Interiors requiring intermittent use of visual tasks limited to movement, orientation, and coarse detail. So start change rooms, live storage, bulk materials, dense storage materials, etc. Then moving down here, normal range of tasks and workplaces. That's probably getting a little bit more towards what we're dealing with. We've got simple, ordinary, moderate, difficult, very difficult. We can have a look here: waiting rooms, school chalkboards, routine office tasks, inspection of medium work, drawing boards, most inspection tasks, etc. Fine inspection, paint retouching, fine manufacturing, grading of dark materials, etc. So we're not down this end of the spectrum, not really down this end of the spectrum either. We're somewhere in the middle. I'd suggest that 320 lux. So yeah, we spoke about lumens. This is expressed in lux. We'll go into that in a minute. So I'd say for our office space, routine office tasks, reading, writing, typing, etc., we'll want 320 lux at the desktop. Now, how do we get lux out of lumens? That's all explained on the next bit. So, using the example, so we've arrived at 320 for our office, but let's say we're here in the classroom, school chalkboard, charts, etc. We'll go to 240 lux at the desktop. So that's this desk we're sitting at today. So we need to provide illumination of 240 lux, but that doesn't equate to the lumen output of the lamps. It's not. So we're not just going to have a 240 lumen lamp go pop your uncle 240 lux. What we'll need to do is we've got this illumination calculation that takes into consideration the coefficient of utilisation, so how much light is then reflected around the room, our light loss factor, so how much light loss do we get from having our light up there to the point at which it gets to the desk, and then also illumination per square metre for our lumens from our lab as well. So typically when we're talking about a light globe, we refer to that as a lab. So to do that, we use this equation. So our lux equals lumens per lamp multiplied by coefficient of utilisation multiplied by light loss factor divided by A, which is our square meterage per lamp. So many of you probably thinking, well, you signed up for drawings, not for doing algebra and complex equations. That's fine. It's all pretty much broken down for you here. So in this example here in the classroom here, we need 240 lux. So 240 lux equals our lumens per lamp. That's what we don't know. We've been given our coefficient of utilisation and our light loss factor. Let's say, for all intents and purposes, that's not going to change. So for your office space, you've got exactly that height of light globe and exactly the same sort of reflectance in the room. So we're going to use exactly these numbers in your case. And feel free to use these numbers further on from here as well as just a general guide. So, and then we've assumed 250 square metres. So we've got 250 square metres of office space or classroom, let's say. Then to get our unknown, so our lumens per lamp, you interpolate that equation. So we've got our lumens per lamp equals our square meterage of our room by our desired lux divided by 0.48. Now, obviously that magic to give us that 0.48 down the bottom, that's simply 0.6 times 0.8. But we don't, certainly not expecting you to understand algebra and equations. That's all done for you. The only bit you're going to have to do is 250 times 240 equals, then divide that by 0.48, and all of a sudden we get 125,000 lumens required. Then, once we've got our 125,000 lumens, then we go, well, we've had a bit of research, we've done a bit of research into our office lighting options. So we go, okay, we've got these LED light troppers, 1200 long by 300 wide, will produce 4,340 lumens per light. Divide our 125,000 by that, and it tells us we need 30 light fittings. Or you can do it the other way around and you go, okay, well, I reckon I can put 30 light fittings in here, this is how much I need for each, but I suggest it's better to have a bit of a look for light fittings first and go, okay, well, light fittings are producing sort of that 3,200 to 4,600, that's sort of the range you're looking at, and choose a model, then work backwards. So if you wanted to have a quick go on your phones for that equation, I suggest doing that, but it really is a simple, well, I'll do it right now. Sorry, this might be a little bit boring for those watching at home if I put this video up, but what we're doing is just got our phones out, got the calculators, doing, so 250 times 240, so we've got 60,000 divided by 0.48 equals 125,000. Have we got that? Yeah. And then divide that by 4340 equals 28.80 light fittings. So we could actually put 29 light fittings in that room. But given that typically in an office roof space, you have what are called acoustic tiles, which is a ceiling grid system. That grid will happen in 600 by 600 squares, meaning that if you've got 30 light fittings, that will probably work quite well in your roof. So that's 6 rows of 5 lights in each row, for example, or 10 rows of 3, or so. So it works. So even though we need 28.8 lights to achieve that illumination, we can round that up to a reasonable figure rather than having open space lights with the ceiling. Either answer there is fine. So for our work example, using our office space, can anybody tell me what our lux will probably be that we want to achieve? So go back up to our table here.
We need to keep the moderate difficult. So
Yeah,
it's 400, 320.
Yeah, so I suggest going for 320. And then, look, I won't give you the square meterage of the office. So that square meterage, you can work that out by, this by this. Those square meters of office minus that little kind of storeroom in there. But it's not too different from this figure anyhow. So what we'll be doing is we'll be using this equation here, and we'll be having, let's say, 250 square meters, or that square meterage you calculate, multiplied by 320, and then divided by 0.48. As simple as that. And then you've got your lumens required for that, and then divide that by your lumen output for the lights that you've chosen. So the way I'd go about choosing lights for an office space, let's start by Googling. So office lighting. Words you're going to encounter are troppers. So that's not the type of lighting that we have here. That's the type of lighting you typically have within those office ceiling grid systems. These, parabolic shaped lighting bays that sit up inside the ceiling grid. So that's typically what you use, but it might also be some form of strip lighting like this. I think I'm not sure what these would take on one of those diffusers there, whether they're LEDs. They do look a bit like LEDs, don't they? In that sort of LED light off, but can't see them behind those diffusers. But have a look for those office lighting options anyhow, and choose an office lighting option. Get as creative as you wish for that. So typically, that's the only really tricky bit with the energy calculation part. For your air conditioning, now for an air conditioning designer, like a lighting designer, you can really go to town on this, and you can take into account so many factors. Like if you're sitting in this room, we'll take into account the number of people who are going to be occupying this room. We'll think about possibly the time of day that people will be occupying this room. Think about all this whole bank of south-facing windows we've got here and the heat loss associated with that. We'll think about our east-facing windows. We've got any heat gain coming from that. If we had west-facing windows, definitely we'd be thinking about that. Excuse me. So we think about all of those things. Oh, and some of the building fabric as well, our insulation that we've got in our walls, and also the thermal mass floor. That's how an air conditioning system designer is going to be designing a system for this room, and they'll do that in the context of this whole building. We won't be doing that. What we'll be doing is we'll be doing really simple check method of saying that we need a certain amount of cooling power per square metre. That's it. So it's about calculating the square meterage and then multiplying that by the cooling power that we need. So a very general guide is approximately 140 watts per square metre. Now we'll just speak about electricity and electricity use and talk about that in watts and kilowatts. When you look at air conditioning power, that's also expressed in watts. It shouldn't be confused for watts of electricity. Now, a very inefficient air conditioner will require 140 watts of electricity to produce 140 watts of cooling power. But a more efficient system will use far less watts, like let's say 35 watts, to produce 140 watts of cooling power. So that ratio relates to how efficient the system is. So for our energy calculation, we're going to be doing that at 140 watts per square metre. That's how many watts are required. But given that all of that is embedded in that calculation sheet for you, what you have to do is determine the air conditioned space, so the office space and the corridor, and then put that into the spreadsheet, and it will say, okay, efficient system requires this much electricity, inefficient system requires this much electricity. And that's simply it. So if we were to go, let's say we're going to go and buy a split system air conditioning for this room, what we would do is, using the very simple check method, we're not going to be looking into the way, our windows are facing single parts, all that sort of stuff. We would go, right, we've got, how many square metres do we have in here? So it's going to be about 7 by 7. 7 by 7? Yeah. Let's say we've got 50 square metres in this room. Let's keep it simple. So we've got 50 square metres in this room by 140 watts. We've got, probably plenty of people have done it in their head already, but I'm, sort of that computer configuration. What's that?
7,000.
7,000. So we'll need 7,000 watts of cooling power for a split system air conditioner. So that's a 7 kilowatt split system to provide cooling for this room. Now that's quite a small system, but it's quite a small room. And so then we go down to hardly normal or something like that, and then we go, hey, I've got this room I want to buy a split system for, I need a 7 kilowatt split system. That's how it's done. You can read through this if you wish. I think I've explained that in a nutshell. That's nutshell enough. Then also another important consideration, certainly not for, I guess, the designers of the office. Okay, designers, drafters, yes, you will say this is what's happening in there to an extent, we designed for it, but you're probably not going to be specifying computers. But it's a good thing for you to have a think about, to understand that there are different computing options available that use different amounts of energy. Also, part of that is occupant behaviour. If I shut down my computer or put it to sleep when I go to lunch, I'll be saving a little bit of electricity in the process. Or if I spend all day gaming, I'm going to use a lot more electricity than if I'm just reading emails, for example. So that gaming will use a lot of processor, etc. If I'm rendering models or something like that, I'm using a lot of processor. So it's hard to actually compare energy use between computers, essentially, because it gets muddled up by how that computer is used. So there's a great deal of behaviour that goes into that as well. And obviously your your gaming type computers are also set up with graphics cards and things like that for what they need to do, and not so much with energy consumption in mind. Whereas your phone, which is like for most people, it's like a miniature computer, that is set up with the intent that the battery's not going flat every 5 minutes. So this is geared very much towards energy saving. Your gaming computer is not. So it's geared toward performance. So that's essentially what you're required to do for the research task, is just have a look at different computing options. Whether we want to have some particular tower with a screen, or whether we want to use a laptop with a screen, or a tablet with a screen, or some sort of smaller processor with a screen, etc. So have a think about those things. You can also get information on average computer use, so just for general processor loads, and form some comparison. But as I said before, that area, those waters are all very muddied, because it really does depend on average use, and it sort of really comes down to it. But certainly, I can certainly say that if I've got my my computing tower with my screen, that's going to use more energy than if I have a laptop, for example. Because once again, laptops are geared towards being portable, being able to be used out in the garden or wherever without going flat in 5 minutes. Energy saving is an important aspect of those machines as well. Another aspect. So what we're doing an energy analysis for our office building. So far we've looked at lighting that's required for our office. We've looked at air conditioning that's required for our office, computers for our office. We're also going to have refrigerators in those kitchen areas in the office. So we've got 2 kitchen areas in that office. Staff are going to be wanting to have refrigerators, but what we're not going to require for our office are freezers. It's general office use for lunches, etc. So once again, your refrigerators are getting more and more energy efficient, which is fantastic, because they certainly used to be a large consumer of electricity for the house. Also, because refrigerators are not turned on in the morning and turned off in the evening or so, like we leave them running all the time, we don't talk about those so much wattage of a unit like with my heater. A heater we use intermittently, refrigerator we don't. So refrigerator is they're all compared in kilowatt hours per year. So this refrigerator, whichever brand it is, uses 542 kilowatt hours per year. So at 38 cents kilowatt hour, we're probably talking about $240 a year to run that. Once again, for your normal household economics, you're probably thinking about these things every now and again, thinking, okay, well, my old fridge is costing me a couple $100 a year, more than a new fridge. A new fridge is going to last me this long. Is it time for me to get a new fridge? Obviously, if you're running a building like this, that I don't know how many refrigerators we have in this building, probably let's say 10. Those calculations are going to have to be done on a more regular basis, and it's more important to be thinking about that. Thinking, okay, well, our 10 refrigerators, if they're costing us extra $200 a year, that's $2,000 a year. It's worth sitting down to analyse these things on a more regular basis. Refrigerators are also compared by their size, so they're measured in litres. So how many litres can fit in that volume of refrigerator? So what you're not going to do is you're not going to say, well, my old 500 litre fridge is using this much electricity, but there's this new 300 litre fridge, etc. So, and that's what you're required to do in this task, is compare like for like as well. So you're given some direction in what to look for. Also, solar panels. So, yeah, solar panels is something that's not going away. Obviously, because of the cost of electricity, solar panels are getting used more and more and more. So we've got getting another huge bank of solar panels onto this building, but we're at that point now where there are major solar installations going in. So solar farms and SA Water now. So SA Water is one of the biggest users of electricity in the state. They're going to have their own solar farms to run all their pumping. So that's going to be a massive game changer for energy use within South Australia, and something that has to be, I guess, incorporated into the grid and how that's managed. It doesn't come without its challenges. Obviously, when you start imposing all of the loads on a grid in the opposite direction than what it was designed for, you get some issues, etc. So obviously, our grid, is changing to cope with that. But another thing that solar panels have done is they've opened up the availability, or when coupled with battery packs, for you to be building in areas where you previously, wouldn't consider building. So for myself, I've done a lot of work out on sheep stations, cattle stations, where you're a long way from any electricity grid, and so out there you run diesel generators all the time. So it's just a constant noise in the background of the homestead, this running the generators. But a lot of stations have moved now to having banks of solar panels, batteries. It's all lovely and quiet. They're quite expensive. You're probably talking about $1,000 plus for a system that's going to be supplying you with enough and a regular supply of electricity. But because the cost of bringing electricity long distance is also very expensive, especially here. But that's in large part because of the way that our electricity networks are structured. It used to be publicly owned, and it was supply and infrastructure all publicly owned. Then supply sold off or deregulated, so anybody can be a supplier. And then the distribution networks sold off to two companies, Electronet and SA Power Networks. Electronet with all the big infrastructure, SA Power Networks with all the smaller infrastructure like 415 and 240 volt. Because they're privately owned, they're not really providing a public service. So if you want electricity to your place, you have to pay what it costs, and that's it, or more than what it costs, because they have to make a profit out of their investment. I've found certainly the dealing with SA Power Networks, it's not so much a public service. It is very much on their terms when they want to do stuff, and pay plenty of money for that. So fortunately. But that's the system we've got. But one of the side effects of that is, let's say, let's say we were going to have to, we bought a block of land so in the hills, something like that, and we had to run power for 200 metres. It gets very expensive to run power that longer distance, because it's not just that we have to go, all right, this is how much it cost me to run power for 10 metres and then multiply that by 20. When you supply power, let's say at 240 volts, and you run that for a longer distance through a small cable, you get voltage drop over that small cable. So to compensate for the voltage drop you get over distance, you have to have a fatter cable. The longer the distance you're running it, the fatter the cable. So if I was running power for 50 metres or so, I need a little one. Running for 200 metres, I need a big one. And so then you've got 200 metres of that fat cable to run. It starts getting quite expensive. SA Power Networks aren't going to pay for that. You have to pay for that, obviously. So that's where standalone systems come into being. So that's a space, I guess we haven't seen it. Well, we've had a bit of development in terms of lithium-ion batteries coming on the market. So you've got small packs that can store a lot of energy in a sort of visually attractive fashion, and it costs that $15,000 or so per pack to supply your house with energy. So there's been a bit of development in that regard, but not really massive development in batteries to make standalone the really desirable option. But it's sort of on the cusp of that. What we might see is when we do get enough development in that technology, or take-up of that technology, and price point comes down to a point where, okay, having a standalone system is far more economically viable than being connected to the grid, I think we'll get a major shift happening at that point. But that's definitely a consideration and something to be aware of as designers, or as designers and homeowners, or home occupiers. Do we want to be connected to the grid? Do we want a standalone system? And currently also the state government are giving rebates for batteries as well. So your standalone systems, I think you can do that for about 7 to 10 grand. So it's becoming cheaper, sort of on that cusp of that. So that's your, and other forms of alternative energy supply, wind power as well. We can have wind generator on your property, but typically the way of producing power for yourself at home is going to be solar panels, also known as photovoltaics. The other thing about photovoltaic system is, you probably would have seen it on TV or social media or so, that you can get a 3 kilowatt system for $2,500, fantastic, fully installed. That 3 kilowatt system isn't going to produce 3 kilowatt hours in an hour, typically, because we don't have 100% solar radiation hitting those panels and producing the electricity. We actually have far from it. So we've got this table here showing your different degrees of solar radiation that hit your solar panels. So let's say, in Adelaide, on average, our photovoltaic system will produce 4 kilowatt hours a day. So that's a 1 kilowatt system getting, daylight for on average 10 hours a day. It produces 4 kilowatt hours. So it's producing 40% of its potential kilowatts if we had 100% solar radiation. That's for Adelaide. If we're in Brisbane, we've got a bit more cloud cover happening in Brisbane, tropical location, or getting into the tropics there. But if we put that same system in Alice Springs, for example, not much rain, not much cloud cover there, we get more solar penetration for it. So a little bit of adjustment has to happen. But typically what people will do is they'll put on the largest system they can anyhow. The major limiting factor with that is the supply of electricity. If you're grid connected, that supply to your house comes in typically as single phase or 3 phase. Single phase is 240 volts, 3-phase is 415 volts. SA Power Networks lets you do a 5 kilowatt per phase. So if you've got single phase coming to your property, 240 volts, well then you can put a 5 kilowatt system, 5 kilowatt solar panel system on your roof. If you've got 3-phase, you can put 15 kilowatt system on your roof. That's pretty much it. I've got a place where we've got 2 phases coming in. That's really rare. Doesn't happen often. It was set up in strange fashion. But yeah, typically that's it. So most of your residential properties about the place, it will just be single phase coming in. You'll see some signs about in this building here we've got 11,000 watts coming in certain places because we used to run big gantry cranes, all that sort of stuff. But you'll also see signs about the place saying 415 volt. So you know that there's 3-phase power supplied to those sections. So because of that, 11,000 volts connection here, that means you can just cover the whole thing with solar panels like that. So that's if you look at a system in its entirety. Obviously, you've got different types of solar panels and different wattages provided on those solar panels. A typical one is 400 watts per panel. One panel can generate around 200 watts, which equates to 0.8 kilowatt hours. In Adelaide, it's 200 watts multiplied by 4. So I think we've spoken enough about grid versus standalone. So this is your Excel spreadsheet for calculating that. That one does. Underneath there, it's got the solar panels included in there. It will tell you how many solar panels for an inefficient system. It will calculate this is how many solar panels you need for your inefficient system, or this is how many solar panels you need for your efficient system. Once you do all that, and then you calculate how many solar panels you can actually fit on the roof, it will give you a bit of an idea of can you run an inefficient building from the sun, or do you have to upgrade that building to match the number of solar panels you put on there? It'll give you some insight into that. Now, as part of it, you have to choose a 500 litre refrigerator. So what is the best approximately 500 litre no freezer refrigerator? How many stars and what energy is used each year? We need to go to a few different areas to find out that information. The first bit is we'll go, is that link going to work for me in this room? No. So, no. But I can grab it, copy, move things around. Oh. So we'll get there eventually and pop it in here. Get there eventually. So you're given this link to the energy rating calculator. Sometimes we'll show PowerPoint, sometimes copy paste. So we're looking at a 500 litre fridge. So in that step-by-step guide, I produced some little notes to remind you of what we're about to talk about now. But basically what it says in that step-by-step guide is do use this drop-down arrow and go to all models, because we can search on refrigerators. We can go, oh look, I like Fisher & Paykel, I want to match my dishwasher, blah, or we can go, no, we're just getting these for the office. What we're worried about is efficiency. Don't care about the brand. So we'll go all models. We'll go fridge only. We can select configuration or not. It's not a requirement for the assignment. But what we want to do is we want to narrow down our range of our capacity. So, because we need, there we go. We need to have approximately 500 litre fridge. And so by doing that and then apply a filter, we get a series of different refrigerators arranged in the most efficient at the top, going to the least efficient for that. So we've used that energy rating calculator to find our fridge. So if we wanted to go, so let's go for our most efficient, so 494 litres, that's close enough to 500, that's fine, let's go for that. Grab those, well, I haven't actually tried it for this model, well, I'll grab all of that, copy, take out that little, and search for that model. There we go, specifications and manuals, Sub-Zero appliances. Fantastic. So we get that information, we put that in our report, say we've chosen this particular model, and then bear with me, I haven't been to this website before, search this particular model, but what we want to do is we want to find out annual kilowatt usage. So, design guide, no, probably not. We're looking more for, oh geez, you got CAD models of this refrigerator. That's cool. But what I'm looking for here are specifications for that.
There is a model.
Did you see one?
There is a model with detail. Yeah, in the left, to the left. Fluid details. Maybe you can find something.
Yeah. Where was?
Below
On the left.
Oh.
On the fridge.
Oh, product details. Thank you. Yep. Yes, that might have more information. We go. No. So I haven't chosen a particularly good one to research. I'm sorry, but yeah. So maybe don't research this one. Anyhow, spend a bit of time. Typically, you're able to find what the annual usage is for your refrigerator. If you get to this one and it's taking you too long to find the energy usage, will maybe go to the energy calculator and choose your model. But you should be able to find your energy usage fairly quickly and easily on their websites. Typically, it's quite available there. So that's bring up our energy information again. So that's what you're going to have to do for your refrigerator, for your task, is get a refrigerator, note down how many stars it has, get the name, do a search on that and find out what its annual electricity usage is. So for your office lighting, well, we've been through that process already. Although what you'll also need to do is do a bit of research on your office lighting and provide these details within your report. So say this is the office lighting which I've chosen, and probably what you want to do is do a snip just like this and put it into your report, because it shows everything. It shows all the dimensions, input voltage, etc., but also the light output. So it says we've chosen this one. It's got that much light output. That matches in with my analysis that I've done to say I need X many lights producing this many lumens that require this many watts. Then for your amenities lighting, much simpler. Just research a globe that will produce at least 1400 lumens. It's easy. Spoke about our solar panel rooftop calculations earlier on. So arrange them in these banks. So that's a bank of one. Probably want to have another row there next to that, a bank of two. And we'll want to be filling this whole roof space with 600 mil gap around the edge and 600 mil gap between your banks of two. And that's it for the energy analysis of our building. So we'll get all of those figures and we'll plug them in. I'll see if I can find our Excel spreadsheet buried down here somewhere. I can probably minimize all these ones to get to that. There we go. So we've got our spreadsheet happening there. So we'll put in our square meterage for our air conditioning. We'll put in the average electricity usage watt rating for our computer. So you'll find some commentary on that. Once again, I'm not fixated. There's no actual correct answer. The correct answer is that you've done a bit of research and come up with this is my more efficient approach. But let's say that's 40 watts. It's going to look no, so 40. Fun. Yeah, this keyboard. Anyhow, so then bit of a trick here. So lighting 60 watt fluorescent globes. So how many of those do we need? So you'll be able to have a look back into that electricity information. You go, okay, our fluorescent globes are producing this many lumens. And then any idea what the watt rating is of a 60 watt fluorescent globe? Give you a hint, it starts in 6, ends in 0. Yeah, 60. Yeah, because we've got a 60 watt globe, right? So, whereas our low watt LED, we've calculated how many of those we need and how many watts that is. That's for our office space. Then our incandescents, 21 of those. For that amenities lighting, so incandescents, we use 100 watts to produce those lumens. LEDs, let's say it's 15 watts to do those. And then our refrigerator and average annual, say 215. Yeah, the keyboard's not really doing it. 15. No, all right. But we'll put in our figures there and it will give us our total cost of electricity for the year. And then it tells us how many solar panels we need to produce that amount of electricity per year and our cost of solar panels, etc. Have a good muck around with it. So we've got another couple of weeks until this is due. So if you want it tonight, tomorrow, over the next few days, just got a little time for asking some questions about that. But should be relatively simple. Don't say. Okay. I'll stop that recording at that.